Okay, let's start. Today our topic will be about basic semiconductor junctions. And actually the first part of our course, which was devoted to the fundamentals of kinetics in semiconductor, was quite complete. And now we are ready to deal with some applications. And the structure of the course is the following: that we first learn the basics, first see how the transport in semiconductors like current and at fixed electric fields and temperature gradients can be described, and then we will apply this knowledge to model various semiconductor devices, starting from the very simple ones, and followingly we'll deal with some low-dimensional systems and modern, more complicated devices. So the topic today will be about basic semiconductor junctions, how to deal with screening and transport in them. And first of all, I would like to formulate the system of drift-diffusion equations, which is the system of equations that follows under some approximations from Boltzmann kinetics, and which is quite well solvable at in several situations. Then we will deal with the junction of metal and semiconductor, which is called Shotkey Junction after the name of its inventor. And we will first consider the electrostatics of this junction, how the potential profiles are formed when we contact a metal and a semiconductor. And then we will deal with electronic transport in such a junction. Actually, the contact of metals and semiconductor is very important, because you know that all devices in electronics, all devices in processors are based on semiconductors, but the wirings and the conductors in our houses and in the plugs are all made in metals. So somewhere in the circuit on the chip they should connect metal and semiconductor, and some very interesting phenomena can occur under this type of connection, and we will study how it works. First of all, I would like to remind that we have obtained some very basic equation relating the current at given point of space and electric field. So could you focus on the board more, because people should look onto the equations. So several weeks ago we have found that electric current under application of uniform electric field contains the two components, one of which is called drift component, and it is given by equation J, current density, equals sigma E, where sigma is the electric conductivity and E is the strength of electric field. But further, we have corrected this statement and we have accounted for the so-called diffusive current. Diffusive current is proportional to the gradient of carrier density, but carrier density is proportional to the local Fermi energy EF. And we have seen that if we solve the kinetic equation carefully with the account of Fermi energy non-uniformities, we will get a very simple correction. The gradients of electric potential should be always changed to the gradients of electrochemical potential, which is the electric potential minus Fermi energy divided by elementary charge. So this replacement is always valid whenever you have non-uniform density in semiconductor. Now there is some modification of this statement. Previously, we have considered the sample to be uniformly doped on the average, and there were small, quite uniform electric fields and small, quite uniform gradients of Fermi energy. The drift diffusion approximation tells us that current at each point of space x is proportional to the electric field modified with the count of diffusive current, and this electric field is taken at given point of space. So this should be electric field at given point. And the conductivity is taken also at given point. This looks quite trivial and is consistent with our everyday life understanding of transport, that current at a given piece of metal is proportional to the conductivity in this part, in this portion. And if we have non-uniform resistivity, the current at the given point would be proportional to the conductivity at the given point. But strictly speaking, this approximation doesn't follow so immediately from the solution of kinetic equation, because when we solve the kinetic equation, we have neglected the terms with derivatives. So you probably remember that this equation appeared when we solved the equation like velocity multiplied by electric field minus elementary charge multiplied by derivative of equilibrium function with respect to energy equals the sought for distribution function divided by momentum relaxation time. So here we remained only the force term in the kinetic equation and the collision term, and we have neglected the term with special derivatives. And this was the crucial assumption, because this term, strictly speaking, should be there when fields are non-uniform. And this is the key assumption of drift diffusion equation. You can solve it locally at each point, assuming that the field is uniform in the vicinity of a given point. And then apply the result J equals sigma E at each point of space. This is the assumption of drift diffusion equation. Here I introduce the so-called Quasi-Fermi Level, which is nothing but Fermi energy minus E phi. This Quasi-Fermi level will govern the current at a given point of space with simultaneous account of drift and diffusion. And here we can extend the expression for conductivity as mobility multiplied by carrier density multiplied by electric charge. So this equation is valid for description of transport in non-uniformly doped semiconductor. Still, I would like to focus more on the criteria of validity for this approximation. How do you think? Well, when this approximation to carrier transport in semiconductors is valid, when we can neglect the terms with spatial derivatives in kinetic equation, and actually what would be the relation between current and electric field if we solve the kinetic equation strictly? Does anybody have such assumptions? Maybe very simple assumptions from your everyday life. Don't be shy.
Could you please repeat the question?
Yes. So we have stated that the current at a given point of space is proportional to the gradient of electrochemical potential at the same point of space. This result was obtained when we neglected the terms with spatial derivatives in kinetic equation. This neglect should be justified under some assumptions. Which are these assumptions? Which are the criteria of validity for the drift diffusive approximation that the current here is proportional to the electric field at the same point? Of course, it is valid if the field is really uniform in space. So if the field is constant everywhere, this approximation is valid because it doesn't matter at which point you take this constant field. But if the field is non-uniform, like you have some blade type electrodes with sharp edges, then the field is definitely non-uniform, and this approximation may break down in some very non-uniform fields. When it can break down?
On the borders.
What?
On the borders of the field.
Well, that's a very good and wise answer. Definitely at the borders and at the boundaries of the samples it doesn't work, because there the kinetic equation should be supplemented with some boundary conditions, and I didn't expect this wise answer from you. Actually, it also can break down in the bulk when the field is very strongly non-uniform. How strong should the non-uniformity of the field be for this approximation to break down in the bulk? Okay, I will formulate it and you will probably guess that it should work. The electric field shouldn't change very much at the distances equal to electron mean free path. In other words, the relative change of electric field, its gradient, normalized by the field itself, should be much less than 1 divided by length of free path. Or in other terms, it should the free path is the carrier velocity, either thermal velocity or Fermi velocity, multiplied by momentum relaxation time. If this inequality is fulfilled, then the drift diffusion approximation works fine. And if it is not fulfilled, the relation between current and electric field becomes more complicated. I will sketch it quite quickly, and still it is a very interesting exercise to solve the kinetic equation without neglecting this derivative term and to find the true relation between current and electric field in semiconductors. It is very scarcely covered in the textbooks, but it is a very interesting and simple example. So let's see what happens next. The real relation between current and electric field in semiconductors is non-local. It means that the current at given point is the convolution of electric fields at some different points multiplied by some convolving conductivity kernel. The conductivity kernel depends on two arguments. It depends on the observation point x and the points where we collect the electric fields x prime. And if we try to paint these two terms, the conductivity depending on two coordinates and the electric field depending on one coordinate, the sketch would be roughly the following. The conductivity kernel depends mostly on difference between coordinates x and x prime, and it decays abruptly when we deviate from zero. So it is a peaked function. It has a very sharp peak, and the electric field is typically a smooth function. So typically, when we integrate the conductivity and electric field together, only the electric field at these points makes sense, and we restore our local approximation to the carrier transport in semiconductors. So in most situations, the conductivity kernel sigma x x prime can be approximated as Jude conductivity, n e squared tau divided by m star multiplied by delta function of x minus x prime. In most situations, it can be approximated, so it looks like it is a strong peak, the area under which is equal to Jude conductivity. Therefore, the approximation of this conductivity kernel by a delta function is a good approximation in most situations when the electric field is smooth. Of course, if the electric field is non-smooth, then it doesn't work, and you should take the so-called non-locality, the spreading type of conductivity kernel, to be important. Please ask any questions here, because this is a non-trivial part and I hope you understand it. But if don't, please ask. Okay, if no more questions, I will sketch briefly how can we obtain this relation between current and field in when solving the full kinetic equation without neglecting the spatial gradients. And probably it would be a good exercise for the home task. Those who will be able to solve it will get an increased score for the exam. To do this, actually we should write down the kinetic equation for without neglecting the terms with spatial derivatives, and retain them exactly. The only thing which is non-trivial, that we should split the distribution, the full distribution function, into the distribution function for carriers that move from left to right, which have right moving velocities, and to the carrier that move from right to the left, the so-called left moving carriers. These carriers have equal moduli of velocity, but the sign of the velocities could be different. So this difference is reflected in the sign in the kinetic equation here. And this equation has a very simple solution. This is actually a differential equation of the first order with some non-trivial source term. These terms are source terms. Well, this has a very simple structure. I hope you were able to solve this in the course of differential equations, like constant multiplied by first derivative plus function without derivative equals some function s, which is known. This is solved exactly at any type of function s. The meaning of splitting this equation into the equations for the right moving carriers and left moving carriers is that physically they should decay in opposite sides. For example, if we inject the carriers from left to the right, they should decay when upon the direction of motion. If we inject the carriers from right to the left, they should decay according to the direction of motion to the left. And these two decays are described by two different exponents with different sign. Anyway, for each groups of charge carriers, these equations can be solved. And the solution is given by a very simple convolution of electric field multiplied by such exponential propagation kernel. The propagation kernel is the exponent of coordinate difference divided by velocity multiplied by momentum relaxation time. But velocity multiplied by momentum relaxation time is nothing but free path. So we have already seen that the distribution functions created by electric field are indeed the convolutions of electric field at other points multiplied by this exponentially decaying kernel. This is not yet the conductivity, this is just the distribution function, but to find the conductivity we should just take the velocity and average it over the distribution function. The right moving carriers have positive velocity, the left moving carriers have negative velocity, and we should integrate it over all the angles of propagation. The result would be the conductivity. So the result would be the convolution type expression that we obtained before. So if you make this calculation, the sum averaging over momentum up to the end, you will get that current at a given point of space is indeed the convolution of conductivity with electric fields at different space points. And simultaneously, you will obtain the expression for the conductivity kernel. And you will see that it rapidly decays when the difference between coordinates becomes larger than mean free path. In all further calculations, we will assume that it is valid. We will assume that the field doesn't vary strongly at the distance order of mean free path. But in some situations, it will be invalid. For example, does anybody know the free path of electrons in metals, just by order of magnitude? When it is valid numerically, probably some of you will remember the free path of molecules in the air. Actually, these two numbers are of comparable order of magnitude.
50 nanometers.
In air, yes, it is 50 nanometers. In metals, it is quite shorter, but yes, probably 10 of nanometers in metals is a good estimate. And because electrons in metals are denser than molecules in air. But this can depend on the purity of the material and on the temperature, but free path in kinetics problems can range from tens of nanometers to tens of microns. In very clean semiconductors of extreme purity, it can reach up to 10 microns. And there are some kinds of semiconductor devices that are shorter than these mean free paths. And for these types of the devices, the drift-diffusion approximation, the approximation of direct proportionality between current and electric field, would be invalid, because even the device itself is shorter than mean free path, not to say about the non-uniformity of its electric field. But in some other situations, like we have large devices or dirty devices with frequent collisions between electrons and the purities, this drift diffusive approximation would work fine. Actually, you can estimate this mean free path from mobility, because mobility is E tau divided by m, where tau is momentum relaxation time, and characteristic thermal velocity of electron in semiconductor is square root of kT by m. So LFP is thermal velocity multiplied by momentum relaxation time. It's a good home task to estimate the free path at room temperature in silicon, where the mobility equals 1000 centimeters squared per volt per second. Just take this estimate and remember it for your future purposes. What is the free path of electrons in silicon, and when the drift diffusive approximation applies well for silicon-based devices. I believe it is inapplicable for most modern transistors where the length is several tens of nanometers. Okay, any questions here, please? Don't be shy. If no questions, let's try to formulate the final system of drift diffusion equation that we will work with. The first equation of the system is the equation of continuity. The continuity equation in most general form reads as derivative of charge density with respect to time plus divergence of electric current is 0, but for a while we will consider the steady-state problems when the derivatives with respect to time can be neglected. So we will consider for the first time the steady-state transport in semiconductors. And the second equation is just the modified Ohm's law. Modified Ohm's law states that the current at given point is the conductivity at given point multiplied by the gradient of electrochemical potential, or gradient of the Quasi-Fermi level, which is nothing but the Fermi energy minus electric potential. These equations should be solved together to find the charge carrier transport in any semiconductor device with two contacts. The situation is actually not so simple, because there should be one more equation to fully describe the electrical transport in any confined semiconductor structure. Probably some of you remember which one. So our goal is to find the electric current in a semiconductor device having two contacts and some doping profile. Probably it would be non-uniformly doped. It is doped at the contacts and undoped in the middle. Our goal is to find the current density, the current voltage characteristic. We of course should solve these two equations, the Ohm's law, the continuity equations, but there is one missing point, which is this missing point. Okay, nobody remembers. Probably we have already solved it. Well, assume the following situation. I will try to sketch it, and probably you will get involved in the work. Let us try to find the transport in a piece of semiconductor to find the current voltage characteristic if a piece of semiconductor is connected to the voltage source. And let this piece of semiconductor be doped non-uniformly. It is doped to the density n left in the left section and n right in the right section. And let's assume that the doping at the right is much stronger than the doping at the left. Let the conductivities in the left section and in the right section be governed by the Drude formula mu Ne, where mu is the mobility. Then when we apply the when we switch on the voltage source, the current will flow from positive pole to the negative pole. And here in the right, we should have very strong current because we have very strong conductivity. And on the left, we would have weaker current because we have weaker conductivity. Why this situation cannot correspond to the steady-state solutions of the transport equations? Why this state cannot last forever?
Charge on the boundary.
Or why there would appear some charge on the boundary?
Because our
you can say it in Russian if you have difficulty in English.
Ну, потому что ток справа и слева равны, поэтому на границе раздела допирования должен скапливаться заряд.
Конечно же, это правильный ответ. Of course, this answer is correct. It immediately follows from the continuity equation. If the transport is one-dimensional, then J should be constant because its derivative is 0. It means immediately that we have a large amount of charge carriers moving from the right and small amount of carriers leaving this area. So here we should have positive charge accumulation. There is large amount of carriers moving from right to left and weak amount of carriers moving from left to right. What happens next? This positive charge layer would create extra electric field. I will call it delta E. This extra electric field delta E tries to stop the carriers that are moving rapidly, and it tries to accelerate the carriers that are moving slowly. So, indeed, this equation, like local Ohm's law, should be considered with great care, because for the first time we have written down that current at given point should be proportional to the conductivity at given point. But this situation is initially unsteady. If the currents are non-equal at various points, the steady state the charges would accumulate on the boundaries that will create extra electric field, and this extra electric field would try to make the current uniform in the sample. This is the very non-trivial situation. But we have actually started with the following question. What is the extra equation that we need to supplement these two? I recall this situation intentionally because it hints us what is the extra equation that governs the build-up of this extra electric field. Probably some equation relating electric field to the charge. Probably you remember it. Okay, I hope you remember it, but you just don't imagine that it should be there in such a situation. This equation is the equation, the Poisson's equation, which tells us the relation between the second order derivatives of electric potential and the charge density. So if we have extra charge density accumulated due to non-uniformity of electric field, then it will create some electric potential, and this electric potential will try to uniformize the initially non-uniform current. I have written these equations for the case when we have only one type of charge carriers, namely electrons that were initially sitting on donors, but when donors were ionized, but when the electrons leave the donors become ionized. So it would be sufficient for most of our purposes. So the full system of equations that should be solved when modeling transport in semiconductor devices is the continuity equation, the modified Ohm's law relating the local current and local gradients of Quasi-Fermi level, and the Poisson's equation relating the charge carrier density and electric potential. Altogether, they govern the phenomena of charge accumulation if the field is initially non-uniform, and the effects of drift and diffusion. Actually, the first example that we have considered with accumulation of charge on the boundary could be continued, because this accumulated charge would result in extra diffusive currents that should also oppose the initial drift currents. So there are many intricate phenomena even when trying to solve these simplified drift diffusion equations. Of course, you can try to solve it trivially with some boundary conditions, but you should also keep some figure in mind when trying to simulate the transport in any semiconductor device. This picture is the so-called band diagram. I have already tried to explain what is the band diagram. The band diagram is the profile of electron potential energy in semiconductor when we apply some external electric fields to it. We typically draw several lines. The one line is the profile of the conduction band, the other line is profile of the valence band, and the difference between conduction and valence bands is nothing but the band gap. It is denoted as Eg. What I have shown in this picture. The picture shows the band diagram of some semiconductor sample that has two contacts with fixed electric potentials, phi equal to 0 and phi equal the applied voltage. The applied voltage would be denoted as Vd. D comes from the English drain. Drain is the contact where the electrons leave the semiconductor sample, and the first contact that is typically shown on the left is the source. The source is where the electrons are emitted from. The potential of source is typically taken to be 0, and the potential of drain is typically denoted as Vd. When we apply some positive voltage Vd, the electron potential energy becomes lower at this contact, and the profile of the potential energy is somehow bent. It doesn't necessarily bend itself uniformly. Of course, we could draw a straight line, but we cannot trust ourselves that the real solution of transport equation would give us a straight line, because there can be some effects of charge build-up if the sample is non-uniformly doped, and so on. And the other line that I paint here is the so-called is the Quasi-Fermi level. The difference between the conduction band bottom and the Quasi-Fermi level is the local Fermi energy. The local Fermi energy shows how much electrons do we have here in the sample. If the Quasi-Fermi level is above the conduction band bottom, then this situation corresponds to the metal. In metal, the Fermi level is above the band bottom. And in semiconductors, very often, the Fermi level is in the band gap. So the lower is the Fermi level, the less is the carrier density. Here, when the Fermi level is well above the conduction band bottom, we can say that the semiconductor is depleted, and there is a very little amount of charge carriers. And when the Fermi level is very close to the conduction band bottom, we can speak that the semiconductor is highly doped and it is enriched with charge carriers. So I have shown this picture actually to, first of all, to make some image illustrating the functions that appear in these equations. These Quasi-Fermi level actually show the direction of current. The electric current is proportional to the gradient of the Fermi level. The electric current, the gradient is here negative, and it means that the electric current is moving to the left, and it corresponds well to the situations that electrons, negative charge carriers, move toward the bottom of the band diagram. So everything is well with directions here. But I have also shown this picture to raise the problem of boundary conditions in the drift-diffusion equations. How do you think, how many boundary conditions do we need to solve this system of equations, and what are they? You can think about the order of differential equations that appear here and actually think how many unknown functions we have here.
We have first order for current, second order for potential. So we have one boundary condition for current and two boundary condition for potential. So three.
So your opinion is that the generalized order of differential equation is 3 and we need 3 boundary conditions. But the boundary conditions for electric potential are quite obvious. Phi equal to 0 here, phi equals Vd here. But what about the boundary condition for current, as you said? Where we should take this third one? On the left or on the right? Is left better than right?
It's probably not better, but it's more straightforward to solve equation with time in positive direction. So we need in the left.
Okay, your opinion is actually quite physical. If we raise the left contact by potential energy and you inject electrons from left to the right, then you should take this boundary condition for current at the left. But unfortunately, this answer for current is wrong, because the current is a sought-for function. We cannot impose the boundary condition for current because we don't know the current. our goal is to find the current by solving these equations. The correct answer is that we are looking for three functions. The first is electric potential. The second one is the current. But there is but it is a vector, but in one-dimensional problems it is just one function, jx. And the third sought for function is the carrier density. Because in the previous example with accumulation on the boundaries, we have seen that the charge can accumulate on non-uniformities of the sample. And actually, when we write the diffusive component of the current, we immediately take this carrier density under the gradient sign. Actually, the gradient of the Fermi energy is related to the gradient of carrier density, where gradient of carrier density divided by density itself is nothing but minus gradient, gradient of Fermi energy divided by kT. It follows from the Boltzmann distribution M equals effective density of states in the conduction band multiplied by exponent of Fermi energy divided by kT. So here we related the current via gradients of Fermi energy, but we can equivalently formulate it via gradients of carrier density. So carrier density is also an unknown quantity. We have three functions. There is second order differential equation for potential, first order differential for current, and again first order derivative for Fermi energy, but it is equivalent to the first order derivative in carrier density. So we have three functions and altogether like 4 differential operations. 2 for electric potential, 1 for current and 1 for the density. So we will need 4 boundary conditions. The 2 boundary conditions are for electric potentials, and the other 2 boundary conditions are typically for the doping at the contacts. How much electrons are there in the contacts? And the contacts are typically doped so strongly that they remain neutral, and the contacts on the left and on the right typically remain neutral, and the typical boundary condition is that n at coordinate equal to 0 equals the nominal density of donors, and the n at x equal to the length of the sample equal the density of donors. And so the remaining 2 boundary conditions are the boundary conditions on charge carrier density, and it is typically known at the ends of the semiconductor structure. This is the formal, this completes our formulation of drift-diffusion equations. Do you have any, and yes, you see that these boundary conditions are symmetric. The left is not better than the right, and well, it's quite good. Despite we inject electrons from the left, then they collide, and they all the sample becomes quite uniform. So left is not better than the right in such a formulation. Do you have any more questions? Okay, if no more, let us try to apply this system of equations to the transport in the simplest junction that we can have in nature. This is the junction between metal and semiconductor, and I think we will cover the electrostatics of this junction. How does the potential profile form there, and we will try to derive some simplified expressions for the potential profile, and then probably we will have some time to cover the transport. So what happens when we bring metal and semiconductor in contact with each other? Here we have the band diagram of this structure. The dashed line is the vacuum level, the energy level of a free electron in free space. When we deal with a metal, all metals live like they are in potential well, and there is some work needed to extract an electron from metal to vacuum, which is the work function of the metal. It is the distance between Fermi level and vacuum level. And on the left we have a semiconductor. This semiconductor is considered as n-doped. And typically for n-doped semiconductor, the work function, which is denoted here as phi s, is less than phi m. N-doped semiconductors have smaller in modulus work function than the work function of metals. It may seem as metals are deeper potential wells for electrons compared to n-doped semiconductors. Which physical phenomena would happen when we bring these two in the contact? Do you have any opinions? There will be some redistribution motion of charge carriers where the electrons would move. Well, all bodies try to find the minimum of their potential energy. So if there are some electrons on the donor levels or in the conduction band in semiconductors, they have typically higher energy than the Fermi level in metals. So they will try to move from semiconductor to the metal. And they will try to fall from the higher Fermi level to the lower Fermi level. This is equivalent to water in connected bulbs. If there are two bulbs connected by a pipe and there is a higher level of water in one of them compared to small level of water in another one, then there will be a water flow from the higher level to the lower level. But there are some important differences between semiconductors and water reservoirs, because in water reservoirs there will be the equilibrium will occur only when the levels would become identical. The difference is that water is not charged and electrons have charge, and their charge can play an important role. When electrons leave the semiconductor, they retain a positive charge behind, and the metal becomes negatively charged. It means that the potential energy of electrons in metal would be raised, so it would be equal to initial plus the change in potential energy due to charging, and the charging will raise all the bands of the metal higher, and even the vacuum level here would become higher due to this extra Coulomb energy on the and what we will have in the end, this Coulomb energy would raise the Fermi level in metal and the conduction band bottom in the metal and the vacuum level near the metal, such that this redistribution would become finally unfavorable. So what we will have in the end, the band diagram that we will have in the end, is that all levels in metals have risen, and actually some energy and the energy levels in semiconductors have risen, so such that an extra electron which would like to diffuse from metal to semiconductor experience a high energy barrier. So initially we started with diffusion of charge carriers from the material with low work function to the material with large work function, and this diffusion stops whenever the energy barrier due to redistributed charge appears. The height of this energy barrier, which is measured as built-in voltage, is easily calculated. You can easily calculate it by noting that the distance between conduction band bottom and the vacuum level is constant. So by considering this, this equilibrium, you can find that energy barrier, or the built-in voltage, is nothing but the difference between work functions of metal and semiconductor. So this barrier acts to compensate the work function difference between metals and semiconductors. And these work functions can be found in various tables. For metal, they are tabulated. For silicon, germanium, gallium arsenide of various dopings, they are tabulated too. There is one more hint that I should tell you in advance, is that this rule is not always fulfilled. There are several situations when the surface of semiconductor can be charged when due to the existence of surface states. This rule is not fulfilled when the surface is unpassivated and quite dirty. And if the surface states exist, then this rule breaks down. It breaks down for the very often for the contacts of silicon and several metals. But if there are no surface states for some reason, or they are passivated, then this rule works fine. So what will be our next goal? Our next goal would be to find the form of this potential energy profile, or to find the form of the shape of dependence of potential with respect to coordinate when we make such a junction. If the semiconductor is initially doped to the density, to the donor density and D+. We have already faced such problems, and we probably know how to solve them. Assume that the potential here at the left equals 0, and the charge carrier density equals infinity. Then we can write that electron density at some point x is equal to electron density at infinity multiplied by exponent of E phi divided by kT. The larger is the electric potential, the more electrons we have there. Here the potential energy goes up. It means that potential is negative here with respect to the infinity, and it means that this area is depleted. It means that there is a very little amount of electrons here. And so which equation we should solve to find this potential profile? We should solve the Poisson's equation, the second order derivative of electric potential with respect to the coordinate, equals minus 1 divided by epsilon, epsilon 0, the density of donors minus the density of electrons that depends on the coordinate. Now we can, in principle, substitute this expression for the carrier density into the Poisson's equation and solve the resulting nonlinear equation for electric potential with boundary conditions. Phi at minus infinity equals 0, and let this junction point be x equal to 0, then we can write phi at x equal to 0 equal the built-in voltage, which should be negative in the situation under the consideration. This is the straightforward way, but the complexity here is that the resulting equation is nonlinear, and there are actually more complicated situations when this junction is biased with some voltage. So solving the nonlinear differential equation, even to find the distribution of potential, is very often tricky. So there are several approximations to solve these type of equations, which are quite useful. Before proceeding to these simple approximations, I will give you a home task to solve the profile of electric potential in the Schottky junction, solve this nonlinear differential equation exactly. The solution is quite complicated, still it's doable, and you can find it immediately. The simplifying assumption is that the bulk of the semiconductor is neutral, therefore the density at infinity equals the density of donors, and the right-hand side would vanish at minus infinity. I think you can solve this equation exactly, but now we will pass to some approximations. So the typical approximation is called full depletion approximation. Full depletion approximation means that there is some region in the vicinity of the boundary. Its width is denoted by W. And in this region, the amount of electrons is so small that the charge is created only by positively charged donors. So in depleted region, this equation is largely simplified. In this region, we can drop the electrons and we can retain only the charged donors. Of course, this approximation is not valid everywhere, because it is definitely invalid in the bulk where electrons compensate the donors. But we can assume that there is some region with W. We will find this width where the electrons are indeed not so many. And well, let's try to proceed this way. Instead of solving the complete equation for electric potential everywhere, we write it as a second order differential equals minus 4p pi e divided by epsilon s and d plus in the region between 0 and width, and it equals 0 exactly otherwise. Well, that could be quite good approximation. I hope you catch probably that you have seen probably that I use different units for electric potential. This equation is written in Gaussian units. When trying to rewrite it into the C units, you should replace 1 divided by 4 pi with epsilon 0, the dielectric constant in Coulomb's law. So in C units, it looks like elementary charge divided by dielectric constant of semiconductor epsilon s and dielectric constant of vacuum epsilon 0, and in C units it is 4 pi e divided by epsilon s. So now we can we can simply solve this simplified equation, because in the region of depletion it's just second derivative of potential equals some constant. We integrate it twice and get that phi equals to some constant a plus bx minus 2 pi e epsilon of semiconductor multiplied by nd plus multiplied by x squared. This is the solution in the depleted zone from minus w to 0. And in the second zone, the solution is just 0 electric potential, because we need to find some function which has 0 second order derivative. Of course, it could be a linear function, but linear function means that we have some electric field deep in the contact, but it doesn't correspond to the situation that we have global equilibrium. So we take the solution in the deep bulk as 0 electric potential. What is remained, we should match these solutions gradually. Gradual matching means that not only the potentials at the matching point minus w should be equal, but the derivatives of the potential at the matching point should be equal. It means that this parabolic function should be 0 at the matching point, and its derivative should be 0 at the matching point. But we also have a third boundary condition. We need the height of this potential to be equal to built-in voltage when we take it at the boundary of semiconductor and metal. So we have, it looks that we have 2 integration constants and 3 boundary conditions. Is it something wrong with this situation, or it can be resolved? Well, I reformulate the problem once more. When we try to solve the electrostatics of the Schottky junction in the full depletion approximation, we face the situation that we have 2 integration constants to find the electric potential in the depleted zone, and we require 3 boundary conditions. Can they be satisfied simultaneously?
We have 2 equations.
No, we have 2 integration constants. So we had a simplified equation for electric potential, second derivative of potential with respect to coordinate equals the density created by positively charged donors. We have integrated it twice, and we got 2 integration constants A and B. Still, we have three boundary conditions because we know electric potential at the left, we know electric potential at the right, and we require gradual matching of this parabolic function to 0. So two integration constants and three requirements. How can we resolve it? Okay, this is actually quite a tricky question, but yes?
The width as the additional unknown parameter.
Yes, of course, of course. Yes, you're right. The width of the depleted zone was introduced artificially to make this model, but it is yet unknown. And the width is the third parameter that we have introduced here. So when resolving this function with these three boundary conditions, we get both A and B and the expression for W. I will not do this math here. I will just sketch the result, which is most important, the result for the width. In the Gaussian units, it is given by the first part of expression, and in the C units, it is given by the second part of the expression. So what is the general knowledge about the depletion width that we should know? It is proportional to the square root of the built-in voltage, and it is inversely proportional to the square root of the doping density. And it is quite physical, because doping density shows the ability of semiconductor to screening. The stronger is the doping density, the faster is the screening, and the shorter is the screening length. And if the built-in voltage is large, then you should screen the large voltage from constant value to 0, but you should have larger and larger distance to screen this larger and larger voltage. So therefore the depletion width is proportional to the square root of the built-in voltage. It is not provable exactly, but when the junction is non-equilibrium and we apply some voltage to it, in addition to the built-in voltage, like you bias it with the battery such that its negative pole is attached to the left side. If the junction is non-equilibrium or biased with some voltage V, then the replacement is that the built-in potential should be corrected by the amount of the bias potential. And instead of it, we have the expressions like modulus of built-in voltage minus applied voltage multiplied by the product of dielectric permittivities and divided by the density of dopants. It is not provable exactly, but it is a good approximation, and the full solutions show that it works fine, and we will use it in several situations. So if we have solved the steady distribution of electric potential, then the unsteady distribution of electric potential is obtained approximately by shifting the built-in voltage by the amount of the bias voltage. It is not a strict rule, but it is a rule that typically works. So we don't have much time left, but what we'll do in the next seminar, we will try to find the current voltage characteristic of the Schottky junction. You see that even in the equilibrium, it is doped non-uniformly, so its carrier density is being lowered from big values on the left to small values on the right. And it means that in addition to drift currents, there should be diffusive currents that should be important, and there should be also important the effects of charge accumulation. We will try to obtain the current voltage characteristic that is looking in a very familiar fashion. The current versus voltage is exponential. On the forward stage, when we bias the junction in such a way that its barrier height has a tendency to decrease. So when we push the junction forward, then the current grows exponentially. And the rules of this exponent will be derived on the next seminar. Well, I will announce that we will try to write the modified Ohm's law, where taking into account the full gradient of Quasi-Fermi level. We will supplement it with the expression for the carrier density. We will assume that the conduction band profile varies in a known way, and we will make some tricky integration to get these current voltage characteristics that is possible for numerical evaluations. And probably we will consider some extra examples of applying the drift-diffusion equations in real semiconductors. This is the outline of the next lecture. Do you have any questions, please?
Sorry, can I ask a question about several slides
before? Okay, yes, of course.
When we talk about contact metal and semiconductor.
Yes.
Yeah, and one slide before, I guess.
This?
Yes. Yes. Here we have said that if there are electrons in the conduction band, then they will go into metal. But existing an electron in conduction band means that there are holes in valence band. So wouldn't electrons from metal goes to valence band of semiconductor?
Actually, no. We consider we consider a simpler situation when the existence of electron in conduction band means the existence of empty donor on the donor level. And if an electron is going into the metal, it leaves an empty donor behind. So in initial situation, this empty donor is above the Fermi level in metal, and it doesn't get populated back by electron from metal because it requires an increase in energy. But when we deal with equilibrium, of course, a part of the donors is repopulated back by metal electrons. So the process that you are mentioning, the repopulation of empty spaces that were left behind by metal electrons, eventually takes place. So initially, the direction of flow is only from semiconductor to metal, but this repopulation occurs at the final stage. But it doesn't affect the validity of the equation that we have written. So you can verify that everything that affects the electrostatics is electrons in the conduction band and donors that are partly populated.
Yes, thank you.
Mm-hmm. Okay, any more questions? If no more questions, then I tell you goodbye until the next lecture. I will amend several home task problems, and probably I will, in our file, in our shared folder, and probably I will write the difficulty, how much score can they add to your final exam if you solve them correctly, because today we have faced two types of home task problem, one for exact solution for electric potential in the Schottky junction, and the second one is about the non-local conductivity kernel in real semiconductors. Well, thank you and goodbye.